All right, hello. I'm back. This is Mr. Nix, and we continue with psychology, and we continue with our study of the brain. We have a few more weeks on this, and I hope you're enjoying some of the stuff you've learned. I've enjoyed looking over your work. It's unfortunate that we're not in class, able to interact with one another, but this is the best we can do. Let me start off with a very short video. All right, very quick, very easy. Let me get out of that. Her name is Dagmar, and she's British, and she's undergoing brain surgery. Okay, and she actually is having a tumor removed from the right hemisphere of her brain. And notice that she's awake and she was playing violin. She's a music teacher, and the violin is her life. And the idea is that as they were removing that brain tumor, they were worried that going into the brain and extracting the brain tumor would damage areas of the brain that for her are dedicated to music and specifically for playing the violin. So what they did was they put her in a functional magnetic resonance imaging machine known as a fMRI, and they conducted a test. And they played music for her, and they asked her to play music, and they were able to map the areas of her brain specific to the right hemisphere, because that's where the tumor was, involved in for her playing violin and making music. Okay, and this is just one of the latest examples of the kind of technology, or I should say, an example of the kind of technology we have for studying the brain. And fortunately for Dagmar, she was able to maintain her ability to play the violin with the successful removal of that tumor. Okay. Now, by the way, for most of us who would undergo brain surgery, we wouldn't be awake for that operation. She was, and the reason why she was is because they wanted her to play violin while they were operating on her to see if they were getting too close or too into the area of her brain that was responsible for playing the violin. And they had mapped her brain, as I mentioned before, with a fMRI test, which you see an example of in front of you, which I'll explain in a second. Now, the thing about the brain is it's responsible for all feeling, but it has no feeling. Once you're in the brain, the patient would not be able to feel what you're doing in there if you're operating on it. You have to anesthetize the scalp and the nerves that are in the scalp, but once you get into the brain, there's no feeling. So they were in there, and she could play violin, and she wasn't even feeling what they were doing. Fortunately, that for her was a success story, and I thought that was interesting, and you perhaps would find that interesting as well. But it also points once again to the technology we have for understanding the brain. So what you're seeing in front of you here is a sort of colorized version of an fMRI test given to a person with dementia. We've studied this for seemingly forever now. The dementia in this case may have been caused by Alzheimer's disease. That's one of the diseases that can give rise to dementia. That is the basic degenerative notion that the brain is undergoing an attack of sorts and people are losing their cognitive abilities. Okay, so we've studied that. And what this shows here is that when you give a person with dementia iPod or whatever, and they're listening to music, you can see that the brain, in a sense, lights up. These are the areas of the brain that are very active when music is being played. Now, this, is, of course, is all review. We've done this 1,000 times, it seems, and for you, you're experts on this. But I just want to once again point to the technology because, once again, you might remember this from way back when. Here are two cross sections of two brains, one a healthy, normal brain, and the one below that was decimated by Alzheimer's and the dementia that comes with it, with the memory system all but disintegrated. And way back when, before we had the kind of technology that we have now, in order to understand why a person or how a person's disease or disorder affected their brains, you had to basically look at the dead brain. Okay, you couldn't use the kind of technology that we now have. So now, as we look at people with Alzheimer's and all kinds of various problems, we can see the brain in action thanks to things like fMRIs. All right, that's that. Okay, just a little bit of a segue there from past material to what we're going to do now. And what we're going to do now is take a look at the brain very specifically. And we've been doing this also. Once again, it started with Phineas Gage, the guy whose camping rod blew through his head back in the 1840s, and because of damage to the frontal lobe, his personality changed. Ergo, the frontal lobe must have something to do with a person's personality, judgment, impulse control, so forth and so on. We studied Greg the Last Hippie, whose tumor rendered him fat and hairless, but also blind and unable to form new memories, hence stuck in the 60s. And we studied the brain parts that were affected by the tumor. You just read about HM, the famous patient whose surgery to remove the hippocampus to allay his seizures caused him to be unable to form new memories, and that was proof purchase that the hippocampus was crucial to forming new memories. Although, as you guys now know, when asked to draw a star over and over again, eventually he was able to kind of get it down. He didn't remember doing it, but he had what we call procedural memory, motor skills, muscle memory, that kind of thing. So the whole bottom line there, which many of you caught up on, was the idea that memory might, say, begin with the hippocampus, but it's dispersed throughout the brain and involves a lot of brain systems. Okay, but there is the brain in all its glory. I love this picture because it shows the human brain, 3 pounds basically of fat and water. Normally, if you saw a brain like this, it would be just the gray matter. It'd be gray, basically, but this shows you some of the blood supply that feeds the brain, if you will, that provides the brain with oxygen and nutrients. So it's kind of a cool picture, even though it's a little gross. And see, what do we have here? All right, let's take a look at this sucker. So here you have what is known as the cerebrum, okay, which is the largest part of the brain, and it contains what we've already studied, the cerebral cortex, all of this wrinkly stuff that you see right here. We'll talk more about that in a few minutes. This is also known as the forebrain because it's kind of right on top. It's the big part of the brain. It's the part of the brain you see if you were to take a brain out of the skull, and as we are looking at it right now. There's a couple other notable big parts here. This is the cerebellum, okay, also known as the hindbrain, and I'll talk a little bit more about that. Now here's a brain that's been taken out and kind of laid flat on the table. This would be where the eyes are. This is the back of the brain. If you were to kind of stand this brain up, the cerebellum would kind of fall underneath the cerebrum, which includes the cerebral cortex. So basically, if you run your hand down the back of your head, where your skull meets the back of your neck, kind of right up in that soft spot there, that's where your cerebellum is, all right? And then extending kind of below, underneath the cerebellum, but also extending beyond it, would be the brainstem, which extends into the spinal cord. And we're going to talk about all of these structures right now. Now, let me tell you what's going to happen, all right? So this video here is probably going to be the longest of 2 videos that I'm going to make. And when I say longest, it's not going to be that long at all. This could be very basic stuff. I just want to get a few brain parts under our belts so that you have an understanding of the basic structure of the brain. You've already been studying this. Some of this will be review, but there will be some added information. I'm going to ask a couple of real basic questions in an Edpuzzle about this, and I'm going to submit this to you in the form of 2 videos this week. Right? That doesn't mean a lot of work. Actually, that means less work. I'm going to give you 2 relatively short videos with some very quick, basic, comprehensive questions about the brain. You're going to nail that stuff down. You'll have it under your belts. And then when we go forward, we start getting into more complex material. These brain parts will come back, and hopefully you'll be able to put everything together. So let's start. And we'll start with these 2 images here. This is the brainstem we're talking about, which was the last part of the previous, right, part of the brain or area of the brain that I was talking about. That would be this structure here. You can't really see what we're about to see in a second because it's underneath the cerebellum, but that's the brainstem. And let's talk about what the brainstem does. Now, the brainstem has a number of parts, as you can see, and we're going to talk about what these parts do. By the way, here's your cerebellum, here is your brainstem, and that would extend into your spinal cord, which hopefully you understand what that is, all right? Now, the brainstem is called the brainstem because it's like a stem. It's like a stalk on which the rest of the brain sits. And it's involved in very basic, but obviously very important functions. When I say basic, I don't mean like easy functions necessarily. What I mean is basic survival functions, functions that are primarily part of what we call the autonomic nervous system. I don't know if you remember that from biology, but these are things that kind of happen automatically. You don't have to think about them. It's not conscious. It's just like there. This is what the brain does. So you can focus on other stuff like what I'm telling you and let the brainstem keep you alive and do some other important things. So let's break this down. We'll start down here with something called the medulla, also known as the medulla oblongata because it has an oblong shape. Now, it's not very distinguished in this particular map here because it's kind of embedded in the brainstem, but right where this line ends, this area here is the medulla. Just kind of accept that, please. Now, in the medulla, is involved essentially in keeping your heart beating and controlling your breathing. All right, these are things you don't have to think about. You just do it. It's not like you're sitting here saying heartbeat, 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 right? It's just happening, and the medulla is basically making that happen. And breathing, of course, is also another autonomic nervous system activity that the medulla is responsible for. So you can see the medulla is extremely important because, well, it keeps you alive. You may be in a coma. You may be what they consider to be brain dead in the sense that you're not conscious and perhaps not aware of anything, not taking in any sensory input, but you're still alive. Your heart's still doing its thing and you're still breathing. And, well, maybe there's hope, but at the very least, you're alive. Okay, so I'm going to skip over the reticular formation for a second, and I'll get back to that. But let's move up and talk about this thing called the pons. Now, the pons is another area of the brain, kind of just generally right here. And it's involved in things like bladder control, swallowing, check this, directing eye movements and recognizing facial expressions. It's also involved in sleeping and dreaming, which I'll talk about in just a second. So once again, basic autonomic nervous system functions. Bladder control, I gotta go to the bathroom, right? You learn to control that. It becomes automatic. Swallowing, another autonomic, nervous system activity, right? But think about this for a second. The pons is obviously getting into other areas because I talked about controlling eye movements and recognizing facial expressions. I mean, that's pretty interesting. That's basic, but then again, not so. And it begs the question, why would this consider to be something that is really important, evolutionarily speaking? Why is this something that has to be automatic? Why is it important for you to recognize facial expressions without having to actually think too much about it? It's not as if you look at someone who's really angry and you say, wow, facial expression, yeah, I see that. Okay, that person must be A, B, C, D, angry. No, it's automatic. And of course, you get the point here. The point is that for you to be able to recognize facial expressions is for you to be able to understand someone else's emotional state right off the bat, which is very important for human connection, human sociability, and human survival. And the pons allows you to understand that automatically. So you know if someone is sad or happy or disgusted or, once again, angry, threatening, frightened. Okay, that's important stuff. Controlling eye movements, once again, kind of automatic in the sense that our eyes are constantly taking in visual information. They're constantly darting about the visual space that we exist in, and that is being controlled in part by the pons. There are other brain parts that figure into that, which I'll talk about in a minute, at least in the case of the reticular formation. But the pons, once again, is important in the sense that facial expressions, bladder control, swallowing, eye movement, and sleeping and dreaming. It's involved in that too. I'll give you one basic lesson here before we actually get into sleeping and dreaming, which would be for another video or another screencast or whatever. Here's the idea, all right? We all dream every night, okay? And the pons is involved in that. And part of what the pons is involved in is rendering you essentially paralyzed during what is known as rapid eye movement sleep, REM sleep, a stage of sleep where we do a lot of our dreaming. Not the only stage, but suffice it to say, let's just leave it at that. And of course, our dreams are crazy. I mean, they're wild. They're all over the place. They're scary. They're threatening. They're bizarre, right? And, we don't act those dreams out. We just kind of have them as an internal movie that we react to emotionally, but we're safely ensconced in our bed, lying there, seemingly okay with the world, but maybe actually undergoing a very tumultuous dream. And the reason why it is because the pons elicits chemicals that actually cut off the connection between the major muscle groups and the brain itself, as if, in a sense, you're paralyzed. So even though in a dream you want to run, essentially you can't. And of course, in your dream, in your bed, you wouldn't be running. That would be dangerous. It would wake you up. It would interfere with your sleep. So that's why, by the way, when you're in a dream and you're trying to run, it's almost impossible. The pons is involved in that. The pons basically issues a paralytic substance, chemical, that keeps you from acting out your dreams and basically paralyzes your major muscle groups. All right, enough of the pons. Let's move on to this thing called the reticular formation right here. And it's kind of extending down into the spinal cord. It actually also extends up into other areas of the brain. So the reticular formation actually goes beyond the brainstem, but we still kind of, encapsulate it in the brainstem. So that's how we're going to talk about it. And I'm a big fan of the reticular formation, and it's kind of like the pons in some ways, in the sense that the reticular formation, as you can see in this right image here, is involved in taking in sensory input from the eyes, say from the ears, and then arousing the higher centers of the brain to that sensory input. And I'll talk more about this in another video that you're going to watch maybe next week. But suffice it to say that a lot of these stuff we respond to in the environment from a sensual standpoint or a sensory input standpoint, we do so unconsciously. We can't consciously pay attention to everything in the environment. It is not possible. All right? And so we have the reticular formation to thank in the sense that we can react to sensory input before we're even aware of the origin of that sensory input. So I'll give you a pretty good example, I hope. Let's say you're sitting on the front steps of your house, it's a nice day, and all of a sudden something flies by and you react to it. Okay? Now, it's a fly, or it's a bee, or it's just a leaf, coming down from the tree. And the thing is, you reacted to that movement, which potentially is threatening, before you even saw consciously what that was. You just reacted to it. And the thing is, I'm going to try to do this the best I can. Let's pretend this is a fly. It's up here. You're sitting on your front steps. All of a sudden, it flies by you, and you react to it. You wipe your hands, you flail your hands, you move your head. What the hell is that? And then you say, oh, it's just a fly. Okay, I don't like flies, but whatever. Well, you only saw the fly after your eyes were oriented to what that was, and you said, oh, it's a fly, or it's a leaf, or it's a bee, or it's nothing. But because your reticular formation picked up that sensory input, which is coming in from the eye, it aroused the rest of your brain, if you will, to pay attention to it. So in other words, you detected motion and reacted to it before you even saw what it was. This happens all of the time, and it just doesn't only involve sight, sensory input. It can also involve touch and hearing and that sort of thing. Okay. For those of you who are old enough to drive a car, although driving a car is just one example, because even if you just move through a landscape walking or as an athlete playing your sport, you rely on the reticular formation to arouse you to things in the environment that are important, even before you actually see or hear what those things are. All right, that's the reticular formation. I hope you get it, and we'll revisit that concept soon. So that's basically the brainstem. I want to also talk about a couple more parts here, which are parts of the brain which aren't part of the brainstem. So we've done the medulla, heartbeat, breathing, the reticular formation, an arousal system that allows you to pay attention to sensory input without actually consciously understanding what it is. The pons, which has numerous responsibilities, including swallowing and bladder control when sleeping and dreaming, eye movements, facial recognition. All right, and so that's it. That's pretty much the brainstem as far as we're concerned. A couple other things. We did the hypothalamus and the pituitary gland when we studied Greg the last hippie because his brain had damaged his pituitary gland. We're talking about the master gland, the endocrine system, the hormone release, and controlling basic body metabolism. All of these three structures here, and I'll talk about the thalamus in a second, are part of what we call the diencephalon. Don't worry about that. It's just kind of one of those things that I have to be clear about in case you ever look this stuff up again in the future. They're not part of the brainstem. They're their own separate entity. And we've talked about these two in the guise of Greg the Last Hippie. We talked about these parts in the guise of the brainstem. And now the thalamus, as you can see right here, deep in the brain, kind of like an almond-shaped structure. The thalamus is like a switchboard, all right? Whereas the reticular formation causes you to act automatically to detect things that are important and react to them. The thalamus takes visual, all sensory information, and it kicks it off to the areas of the brain that deal with that particular sensory information. So hence the switchboard. Now, switchboard may not make sense to you because we don't really use switchboards anymore. But back in the day, and this is before my time, by the way, you might have seen this on old movies, I don't know. If you wanted to make a call, you had to go through a switchboard. You
you had to actually get to an operator, and the operator would have to plug you into that number to get to your friend across town. You couldn't just call them up directly. You have to go through a switchboard. All right. In any event, a switchboard is, as the name implies, something that connects two things that go together, if you will. In this case, as you look at the screen, I hope that's what you're doing still, or whatever you're looking at, doesn't really matter. The example still holds. The thalamus says, "Oh, that information is coming from the eye. That's visual information. So I'm going to kick that visual information off to the back of the brain in an area called the visual cortex." And I notice we don't have the visual cortex illustrated on these particular images, but we'll get to that later. But some of you might remember from some of our other studies that the visual cortex is in the back of the brain. That's where seeing takes place. In fact, I think I talked about this when we talked about Greg the Last Hippie. Very similarly, if you are listening to me right now, which I hope you are, that information is going in through your ear, sound, okay? And the thalamus says, oh, auditory information. Let's kick that off to the auditory cortex. So the auditory cortex can make sense of it so that you can hear and understand what I'm saying. So in other words, the thalamus, like a switchboard, takes the various sensory information that you're dealing with and it kicks it off to the part of the brain that deals specifically with that sensory information. All right, let's move on. Okay, a couple other quick things here, and then we shall be done with part one. There is your cerebellum right there, and you can see it over here as well. Big fan of the cerebellum. A couple of cool things about the cerebellum. It's called the hindbrain because it's kind of behind the brainstem and the spinal cord and underneath the cerebrum, including the cerebral cortex. There it is. You can see that very clearly. It contains over half of the brain's entire neurons. In other words, in this relatively small hindbrain cerebellum, over half of the overall neurons of the brain are located here. In other words, you have some very densely packed neural activity going on here. So the cerebellum must be really important. And the cerebellum is almost like its own little mini brain. Now, in the past, when I taught this, I taught that the cerebellum was essentially involved in coordinating voluntary movement and balance. So you can get up and stand on one leg, and your cerebellum allows you to do that. And that's really important, right? Balance, coordinating voluntary movement. Obviously, that's really important. But now we know that the cerebellum is involved in more than that, and hence why I brought up that it has over half of the brain's overall neurons, because it's also involved in thinking, it's involved in language, and it's involved in what we call spatial tasking or spatial skills, oftentimes called visual spatial skills. The ability for you to manipulate an object, real or imagined, in a three-dimensional space. So simply think about, should we ever do this again this year, packing your book bag to go to school. You have to figure out how you're going to fit everything in there. Where is it going to go? How is this folder going to fit with this notebook and my earbuds and my lunch and my pencil case? You can pack that, right? Just like you can put together a puzzle. Just like you can walk around your room. Just like you can close your eyes and envision all four sides of your car. Just like if you closed your eyes, you could have a spatial map of your kitchen and you could successfully walk around it even with your eyes closed. You can look in a mirror and see a two-dimensional reflection of yourself and comb your hair and put on your makeup and do all the things to your own three-dimensional self by looking at a two-dimensional self in the mirror because you know where things are in relation to yourself, right? And that's what we call spatial tasking. It's its own form of intelligence. So people who are really good drivers, okay, people who are really good at geometry, people who are really good at puzzles, these people excel at what we call spatial tasking. And that's what the cerebellum is involved in. Okay, I think we're just about done with part one of this. I just want to show you this because, actually, let's get back, I'm sorry. Cerebral cortex, we've done a lot of this, and you guys know some things about that, and I'll point to this specifically. Here you go, cerebral cortex, okay, as part of the overall section of the brain known as the cerebrum, but that kind of layered stuff on top, all that wrinkly stuff that we would call gray matter if we weren't looking at a bloody brain, that's the cerebral cortex, and this is what allows humans to be fully human. Now, animals have it too, right? But this is where thinking and long-term memory and language and all of our higher order chief executive functions of the brain take place. Okay, this is what makes us smart. And humans are pretty damn smart. Now, we're pretty stupid too, by the way, but whatever. We can talk about that later. But we're also pretty smart. And what we have here is a nice example of the cerebral cortex. All right. And up here we see various cerebral cortexes in terms of different animals, okay, culminating with the human. So humans are sort of the evolutionary pinnacle of the development of the cerebral cortex. And what that means is we have a lot of brain space developed to higher order thinking, problem solving, and impulse control, and overriding instincts, and language, and spatial abilities, and so forth and so on. Okay, so cats are pretty cool. They're pretty smart. Dogs are pretty smart too. Monkeys, yeah, we share 99% of our DNA, so they're cool too. But as you can see, in terms of brain size, and when I say brain size, I don't mean that humans have the biggest brains in the animal world, right? But in terms of the cerebral cortex, the size of the cerebral cortex, the ratio of the size of the cerebral cortex to the body itself, in humans, we have the largest brain. Right? Now, some people will actually talk about dolphins. Right? Well, we're not going to really go there. Suffice it to say, humans have been solving problems for a very long time, and we've evolved, obviously. And what we have here in the shaded area is what we know as the frontal cortex. I'm sorry, excuse me, the frontal lobe, of which the frontal cortex is a part. So the cat's frontal lobe, pretty good, but not that great. Okay, sloping forehead. Dogs, maybe a little bit better, but still sloping forehead. Rhesus monkeys, better, okay, but still kind of a sloping forehead, but not humans. Okay, nice big frontal lobe, which contains the frontal cortex, that is the area of the brain on the surface here that we call the cortical tissue, the cerebral cortex. Okay, now why is it so wrinkly? So you might know this. Check out the wrinkles here and look at the mouse brain. Okay, same parts there basically, but not a whole lot of wrinkles going on. What does that mean? Wouldn't a smooth brain be better? Okay, more attractive at least. But no, the wrinkles are key, and the wrinkles have to do with what we call overall size of the brain and the ability to fit a brain inside your head. Surface area, that was the term I was looking for. So I'm going to give you a demonstration. It's going to be completely auditory, but I'm sure you can use your minds and your spatial abilities and your cerebral cortex as well as your cerebellum to imagine what I'm going to do here. I'm holding a piece of paper. It's an 8 by 11 blank piece of paper. And this piece of paper has X amount of surface area. Okay, we get that? As you probably understand, I just crumpled up that piece of paper, and I am now holding it in a tight fist in a ball, and I can't even see that piece of paper. So what I have done is taken a piece of paper with X amount of surface space, and I've crumpled it up, and I've stuck it in my hand. And obviously, it is now in a much smaller container, if you will, my hand, than it was a moment ago before I crumpled it up. But yet, it's still the same surface area, this piece of paper. So basically what the brain is doing here, the cerebral cortex in particular, is it's folding over on itself to increase its overall surface area as a way of fitting into the human skull so that we can have big brains with a lot of surface area in a relatively small encasement. All right, I think that just about does it for this one. A little bit longer than I thought it would be, but once I get going, I like to talk, and that's where I'm at. So you're going to get another one of these videos later in the week with a couple of questions dedicated to it, 2 Ed puzzles for this week, and you'll be done. See ya. Get to that later.